Hey guys, what's up? Welcome. Today we're going to look at the Newton-Raphson method for solving nonlinear equations. So that would be your quadratics, your hyperbolic functions, anything that is more than power of 1. So cubic. So it is more efficient than closed bracket methods. So let's dive in. Switch screens. Okay. There. So here we're going to demonstrate Newton's method using MATLAB. So we're going to define the function Newton underscore method with these arguments: f, which is the function, x sub 0, initial guess, tol is the relative error that we want, or tolerance. So nmax here is the number of iterations that we want. So let's start. So here is the pseudocode. So basically, Newton-Raphson method is a method where it utilizes the tangent line. And it said that the approximate next value, or the approximate root of the nonlinear equation, is the point where that tangent line crosses the x-axis. So let's code this thing. Okay, let's create a new script. So let's define that function. Function, let's say x sub 1 it. So we will return the values x sub 1 for our root and it for the number of iterations it took. We're going to use it later for printing purposes. So, okay, let's define this function. Okay, I'm going to code this, then I'm going to explain later what the code does. Okay, so we're done coding this function. Oops, why is it double T? Oh no, I'm going to correct this for a moment. Okay, now we corrected the file name and the function name. Okay, so we have a function that returns a root and the number of iterations. So Newton underscore method, our function arguments are the function first, then the initial guess, then the tolerance or relative error that we want or we need, then the maximum number of iterations that we want, and max. Then, so this one seems x, so we need to use the symbolic math toolbox in order to get the derivative of the function easily. So fp here is the derivative. So fp is the derivative of f with respect to x. So x is a symbol here. Okay, so of course this is an iterative method, so we're going to use a loop. So we have our count variable, so how many iterations have been done. Then we have our while loop here, so this is an infinite loop. Then we get our initial guess, store it to x old. We need this later for the comparison of the approximate error with the relative error or tolerance. Okay, so this next line is the actual formula for the Newton-Raphson method, which is the x is equal to x, or x sub 0 is equal to x sub 0 minus the quotient of the original function when evaluated. So this thing here, eval subs, so this evaluates the function. Since we passed a function here symbolically, or we're going to pass a function symbolically, so we're going to need to use the combination of subs. So I think this is substitute, yeah, and evaluate. Okay, so this first one is the original function evaluated divided by the evaluation of the derivative. Then after that, after calculating a value, then we compute the approximate error. So this is your formula for approximate error. We've seen this before in our Gauss-Seidel video earlier. So if x sub 0 is not equal to 0, we need to check, because if x sub 0 is 0, we're going to get a division by 0 error. So we don't compute the approximate error if x sub 0 or x 0 here is 0. Okay. Then after that, we increment the number of iterations. Then after that, we're going to check if we need to end the loop, end the iterations, by checking the approximate error against the relative error. If the approximate error is either less than or equal to the relative error or the tolerance, we end the loop, we end the algorithm. Or if the number of iterations has reached the nmax, or the number of iterations that we set. Okay, so that's our code. Now let's test this. So I've created a script here for calling this function, Newton_method. So still we need to use the symbolic math toolbox, sims x. Okay, then we define our function. In this case, it's x plus f of x is equal to f of x is equal to x plus cosine of x. Okay, then our initial guess, let's say 1, tolerance 0.0001. Okay, and our max number of iterations is 20. So let's try running this code. Let's not suppress the output. Let's see what's going to happen. Okay, we need the command window. So let's call that function Newton. Oh, there, Newton_Raphson. Oh, The name of this should be Newton_Raphson. Okay. Anyway, for now, let's run it. I'm going to change the name later. Okay. So this is going to error. Okay, let's change this first. At the moment, let's use that. Okay, let's run. nr_test. Okay. Let's see what went wrong there. Oh, okay. I forgot to put the put the computed value, the approximate root, into the x1 variable. Okay, there. And the number of iterations, which is just our iter variable. Okay, again, let's try. Clear all, CLC, then let's run. Let's see. Okay, get there. So we got our approximate root at here, negative 0.7391. So this means that if you plug this into this equation, the value of this function, if you evaluate it, it will be close to 0. Okay, or 0. So the number of iterations it took is 8. Okay. So now let's rename this function with the proper name. Okay. Let's rename this Newton_Raphson. Okay. Newton_Raphson. Open this file. Let's rename this to, okay, 6. There. Okay. So now let's pretty print this. Okay. Let's use fprintf. Fprintf. So let's say approximated root that's %f. I want many decimal places, so let's say 0.9f. 9 up to 9 decimal places. It's a float, of course. Let's do \n and x2, our root. Oops, fprintf. Okay, fprintf number of iterations is, of course, that's an integer, so %d. I want 2 new lines and our number of iterations. Okay, let's try running this. Okay, there. I also want to print the original function and the derivative. Okay, so let's do that. Fprintf let's say original function. I'm not sure if this will work. If we put %s here and putting the function. Okay, \n. Then another one is the derivative. fprintf derivative is a string, and that's fp. I want two new lines. Okay, there. Now let's try this again. Clear all CLC. So we have a clean slate. Now let's run this. Okay. So here is our Newton-Raphson method. So for the function x plus cosine of x, so this is our approximate root, and it took 8 iterations. So this is the derivative. I put the printing here so that it's legit coming from the function. You won't think that it's just from the calling script. No, this is actually from the function. So that's why I put the printing of the original function and derivative into this function script here in the actual Newton-Raphson method that we created. Okay, now suppose you entered a constant instead of a function x. What would be the result? Let's try. So let's try replacing f with, let's say, 4. Let's see what happens. So let's run that thing. Nothing. Original function, what is that? And the derivative is 0. Of course, that's an error. Okay? Maybe you use regex for checking that. If checking for invalid input. Okay. What else? So approximated the root, nothing, of course. So let's change this back to F, rerun. Okay. Next, what line of commands show the utilization of the initial value of the root? Okay, so let's go back to our Newton_Raphson script. Okay. So, of course, the initial value or initial guess will be utilized by, of course, this one for computing the absolute error, and of course for the Newton-Raphson formula itself. You plug this to the formula and then make a new initial value and iterate and iterate until the relative error or tolerance is reached, or the number of iterations that we set is reached. So there. So what would happen if the derivative of the function is incorrectly specified? Of course, it will not compute the root correctly, because the Newton-Raphson method needs the correct derivative of the function. So, suppose okay. Let's get the second derivative of the function and let's see what's going to happen. Okay, let's rerun this. I need the command window. Clear all, CLC, for a clean slate, then let's run. It produced a result, kinda. But of course, it's wrong. When we compare it with calculator results, it will be surely wrong. So that's why it's important that the correct derivative is computed. Okay, let's rerun. Okay, we're good. So, to conclude this activity, so we took a look at the Newton-Raphson method. So we implemented it using the symbolic math toolbox for getting the derivative. And then we iterated and utilized the Newton-Raphson formula, which is xn plus 1 or xi plus 1 or next x is equal to initial guess minus f of x over f prime x, or the derivative of x. So then we computed the approximate error and compared it to the tolerance in order to check if we were going to end the algorithm or check the iterations with the specified number of iterations. Then we printed the result. So there you have it. So thank you for watching. If you learned something or like this video, please hit like, share it to your friends, it might help them, and subscribe as well. Also, comment down below if you have a better way of doing it, because you know I'm a newbie in MATLAB. So once again, thank you very much. Have a great day. Bye now.